Hello, everyone. My name is Courtney Brown, and I'm a marketing manager here at Enterprise DB. I'll be your host today for our webinar, Scalable Replication for Postgres. I'm joined by Marc Linster, EDB's SVP of Product and Support, as well as Zahid Iqbal, EDB's Vice President, Replication and Migration Solutions. Before we get started, I just want to go through a few housekeeping items. This presentation is being recorded. We'll be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have a question, please feel free to submit it in the question panel. Today's session is scheduled for about an hour. We expect the presentation to last most of our time today and will allot any extra time for Q&A. If we don't have time to address all the questions, we will follow up afterwards with any attendee whose question was not answered. And now, without further ado, here's Marc.
All right. Thank you, Courtney. All right, so today, as Courtney said, I'm joined by Zahid Iqbal, our Vice President for Replication and Migration Solutions. The way we're going to run the presentation today is I'll talk briefly about EDB, the Postgres platform, and the reasons why replication is of major interest in the context of Postgres. And I'll turn it over to Zahid, and he will talk about the replication server architecture, emphasize our current focus on write availability. We will give a detailed demo of the replication server in action, and we'll talk about the next steps, how everybody on this call can get the software at no cost. Okay, and then, as Courtney said, we'll have time for Q&A, and anything that's not being answered, we'll take care of via email afterwards. So briefly about EDB. Who is EDB? We're really the world leader in open source based Postgres software and services. We've been around for 15 years, shipped products in 2006, and we've been recognized as a leader in this space by Gartner and Forrester. We have over 4,000 customers today. We're present worldwide and heavily invested in the Postgres community. So the 4,000 customers are important because when you look at these names, you can see major customers and big companies around the world. The reason is, on the one side, obviously, we're proud of that, but on the other side, for somebody who's potentially looking at Postgres and at the Postgres technology, you can be assured that these customers are not just using it as, a developer system somewhere under somebody's desk. These are major systems that big companies like MasterCard and Kronos and RSA and Raytheon, et cetera, are using. In EMEA, ABN AMRO has been a long-term customer using it for mission-critical systems. The London Stock Exchange. In Asia, Korea Telecom has published a number of case studies that are talking about very high volume and mission-critical systems. So for anybody who's still concerned about the maturity of Postgres and the maturity of the ecosystem around Postgres, rest assured you're not the first ones, and nobody gets fired for using Postgres, but some people do get fired for not using Postgres. So I think the times have definitely changed. We're present worldwide. The message with this is important because we have a worldwide audience on our call today, and while we're a U.S.-based company, we are present with offices and employees and consultants and support engineers in the U.S., in Europe, and in Asia. Now that has expressed itself in Gartner's appreciation of what Enterprise DB can do. Enterprise DB has been in Gartner's Magic Quadrant for operational relational database management systems for the last 6 years, for as long as Gartner has done this, again after a hiatus that started, I think, in 2008 or 2007. So we've always been in the Magic Quadrant. What's important in the Magic Quadrant today is no other open source relational database is in that Magic Quadrant any longer. They've all drifted out of the Magic Quadrant. You got to think about, again, when you make your decision about Postgres and the partner that you want to choose for Postgres, you have to think about the reasons why Gartner puts people into, or companies into, this quadrant. It's on the one side, the ability to execute, so to be with you 24/7, 365 a year, and in every geography. That's really important. So you have the support organization, you have the services, etc. And then the other part is the completeness of vision, meaning do we have everything that our customers need? Not just from a software perspective, but also from a support perspective, from an engagement perspective, etc. So take a look at this, and if somebody's interested, we can obviously provide the detailed report also. But we're not just commercially interested or commercially invested in Postgres. We have a very, very heavy investment in Postgres open source. So if you're familiar with the Postgres organization, it is led by a core team. There's five members in the core team. No company may have the majority of the core team, so 2 members of the core team work for EDB, and that's Bruce Momsey and Dave Page. But we also have major contributors and what's called committers. So major contributors and named contributors, they're all named on the Postgres or PG admin website, and they're the people who can commit the code and the changes in there. Now, that's one thing to brag about, but the reason why this is important for our customers is they can work with us to influence the Postgres roadmap. And that's a key capability that big customers really value, because they obviously want certain things done, and they want to make sure that they have a way to voice their needs, and that they have somebody to work with to get their needs met, okay, as Postgres evolves. And we're involved in major projects like Zahid, which is a new storage subsystem for Postgres to eliminate vacuum and bloat. So those are types of key initiatives that our teams are driving in the open source community. So I talked a little bit before about the completeness of vision. And the completeness of vision is really focused on, do we have everything that our customers need to successfully deploy Postgres in the enterprise, and to be able to use it for very important and mission-critical applications. That's not just about the database. On the database side, we have EDB Postgres Advanced Server. I won't spend any time on that today. That's basically an Oracle-compatible version of Postgres. And then many of our customers work with straight PostgreSQL, the open source version of Postgres. Then we have tool suites for integration, migration, and management, and deployment options. And again, I won't spend any time on that today. Today, we will talk a good bit about one of the key tools in the integration and migration space. We will talk about our replication tool. Now, just to emphasize a little bit, why is replication so important in the Postgres context? Well, the very first thing that how our customers are using replication today is they offload reporting applications from production applications. And one thing that you have to know about that is that our replication tool can also replicate from Oracle or SQL Server. So XDB 6 or EPRS 6, as it's correctly called, can replicate from Oracle and SQL Server to EDB Postgres or the open source version of Postgres. So it's very easy to offload reporting applications. For example, if you build an application to give your customers order status, you can leave the core system on whatever application it currently is, and then just replicate the order status data and make that available via our website and use Postgres for that. The other really important part is the zero downtime migrations and upgrades, so that customers can say, okay, I don't just snapshot my data, and snapshotting the data can take a long time, but I have a snapshot and then I do change data capture, so that basically my migration time is really, really short. Reconciliation of disparate data systems. So if you have a system running in Australia, another system running in Europe, and you want to reconcile their data with the data that you have from these systems in the US, replication is one way of doing that. And then the last two that are really getting a lot of attention now is read scalability and then write availability. We will talk a lot today about write availability. The reason write availability is so interesting to our customers is because more and more customers are looking for solutions that provide availability of the underlying system 24/7, 365 days a year without maintenance windows, without any downtime. So they're looking for solutions that will help them manage upgrades, updates, underlying system maintenance, addition of capacity, etc. All those capabilities without ever shutting the overall solutions down. And this is true for geographically distributed systems, for global solutions, but also for local solutions. So if you're familiar with Postgres today, you know that we have streaming replication that's built into Postgres. And if you use our failover manager for high availability, there's a technique of how you can apply minor updates, so minor version changes, without shutting your overall solution down. But major upgrades still require that all members of a streaming replication cluster are on the same binary version. So you can't do major upgrades without system downtime using streaming replication. Well, logical replication, the way we've implemented it in EDB Replication Server, allows for that capability. So that's the kind of stuff that gets companies very, very interested in using replication as a solution to drive extreme high availability and to allow you to take Postgres above and beyond what you can do with standard streaming replication, which sort of gets you easily into the 3 nines area. But if you want to go into 4 nines or even above that, there are capabilities that we provide with Replication Server that come in very, very handy. So at this point, I'm going to turn it over to Zahid for the discussion of the architecture and the demo.
Just give me a minute. Okay, hello everyone. Can you see the screens?
Yes, Sid, we can see the screen. Go ahead.
Okay, so as Mark pointed out, we already have the EDB Replication Server in the market that is there for more than 10 years of time and is being used for different needs that Mark already explained. And with the existing solution, we observed that there were certain things that needs to be improved. Specifically, with the existing solution, we had the limitation of a single point of failure around the EDB Replication Server. So in order to get rid of that limitation and to improve on certain other ends, specifically to improve the replication scalability, as well as to provide more extended needs, to meet the more extended needs in terms of the data integration requirements that are growing as part of the IoT context. So we decided to utilize one of the most capable solution in the market as far as the data flow goes, and that is the Kafka framework. So the Kafka framework is a distributed and highly scalable messaging system that provides a fault-tolerant mechanism to enable data flow across different geographies. The key thing with the Kafka is its key capability where it provides the highly optimized I/O capabilities in terms of the zero copy and arrow story format. I will provide more details on the zero copy in a later slide. So as we know that since Kafka is in the market for quite almost for more than 5 years time, and it is being used extensively by some of the non-vendors, like Yahoo is using it, and they have performed certain benchmarks where Kafka was able to scale out without having any limitations. As a matter of fact, the benchmark indicated that there were 2 million writes per second without any impact on the latency. Then in addition to that, another advantage that we have with the new architecture is the capability to offload the data load from the main production database. So with the existing solution, if there is a requirement to add more nodes, then the data load happens out of the source publication database. Now with the use of Kafka framework, the data can be maintained at the Kafka level. So there is a replicated copy, and that copy can be maintained depending on the disk availability. One can set a retention policy, and data will remain there for as long time as required. So for example, if someone has set up a 2-node cluster, and then there is a requirement to add third node, then the third node will be populated with the initial set of data out of the Kafka queue. So in that case, the source database is no more queried. And once the initial data is in place, then the incremental changes will flow through the Kafka pipeline, and any additional changes will be read from the source publication database. One additional advantage that we get is the metadata is now being maintained at the Kafka and Zookeeper level. So the production database does not require any handling for the control data. So Avro serialization format. As I mentioned, that the real GAN that Kafka actually provides is the use of Avro as the story format. Now, Avro is a very compact and fast binary format that provides optimal data storage and data flow without even making use of the compression. So compression is something that will be applied on top of it. So here you can see that there is, in this example, we have got a person record that is of 81 bytes. And we can see that after it is converted to Avro format, it is reduced almost 3 times. The actual size after the conversion is around about 32 bytes. Now that is enabled with the concept of removing the need to transmit schema definition as part of the each message. So once a publication is defined, and then as the messages get published in the Kafka, then initially the schema definition is stored in the schema registry, and then afterward each individual message will only contain the actual data. There won't be any payload in terms of the schema definition. On the consumer side, then the schema is extracted and the Avro message is deserialized. So that is how the data transmission is made optimal. Otherwise, it will require a combination of both schema definition as well as the data. So that is the key advantage that is obtained through the use of Avro format. Here is a high-level architecture of the EPRS 7. Now here you can see that we say EPRS server is a logical term that typically we use when we say when we refer to a EPRS instance. But in reality, there is a loose coupling between the EPRS server and Kafka. So as you can see, EPRS server is running as a separate process, and then underneath there is a Kafka broker that will be running in its own process space, and Zookeeper will be running as a separate process. Now, in order to facilitate the configuration of the replication network, in the initial version, we decided to provide life cycle management to be handled through the EPRS server. So as I will demonstrate later in my demo, when we run the EPRS server, Then internally it invokes the Kafka broker as well as the Zookeeper instances. So the lifecycle of Kafka broker and Zookeeper is controlled through the EPRS server, and user is not required to do any explicit configuration around the Kafka and Zookeeper. In future, obviously, we will provide the additional option where one can actually hook in and integrate with the existing Kafka and Zookeeper cluster configuration, and that will be an added flexibility. But otherwise, it's so much simpler that everything is done behind the scene through the EPRS server. EPRS server provides a REST interface so that there is a CL command line tool that is used to provide the administration and configuration of the replication network. In future, we have a plan where we will provide the GUI level management, and that again will be based on the REST communication. EPRS server runs different producers and consumers depending on the number of the databases that are being managed by a given EPRS server. I'll describe those in more details in the next slide. Kafka basically is used to provide the actual data replication. So for example, in a 3-node cluster, there will be 3 different brokers that will be engaged in a given replication network, and Kafka automatically makes sure that as soon as the data is written on the first broker, then the topic gets auto-replicated to the other brokers. That is being handled by the Kafka framework, and EPRS is utilizing that capability. Zookeeper primarily is being used to provide the node coordination, failure detection, and failover capabilities. So as you see in this slide, so basically, as I pointed out in the first slide, that there is no more a single point of failure. So one can run as many EPRS server as required. The minimum requirement is to run at least 3 EPRS server, and that primarily is related to the fact that we need to make sure that the fault tolerant behavior is available, and to provide a more high available solution. And that is enabled with the fact that when a 3-node cluster is set up, then there is a capability where one can, if one of the server goes down, then still the data will be available on the 2 other servers, and that will keep on running. So the minimum requirement is to have a 3-node server, so that it can actually it can handle a single server failure. In case one of the 2 servers goes down, then obviously that needs to be handled accordingly. Now we can see that there is an association between a given publication database server and the EPRS server. Similarly, there is an association with the subscription database server and EPRS server. There is not we try to be flexible in terms of the context that how a database server will be used. So a single database server can act both as a producer and consumer in a given replication network. So for example, as you can see, DB1 is being used just as a publication database, but on the other hand, we can see that the other databases like DBN2 and DBN1 are being used both in the producer and consumer roles. So it's a matter of how the publications are defined, and then on the joining side, the other database server can be joined either in a replica mode, or it can join both in the write and replica mode. So as the diagram reflects, we can have one can set up just a master replica configuration. Similarly, one can have a master configuration. And obviously, with this new flexible architecture, there is the option to set up a hybrid cluster where one database is acting just in the master mode, the other is acting in just in the replica mode, and then certain other databases can be contributing both in the write and read capabilities. One more thing that I would like to mention is the use of the filter. So by default, everything will, based on the publication set, all the data will flow across the cluster. The user has the option to apply filters on the consumer end. So for example, if there is a requirement where one doesn't want to replicate everything to a given consumer, but want to filter out certain data, then one can apply the filter criteria that is basically conforms to the where clause, and that can be defined at the publication level and can be enforced at the subscription or the consumer level. So here you can see that we have, as Marc pointed out earlier, the key thing that is being getting more focus is the flexibility of the write availability and failover capabilities. So for example, here we can see that we have a 3-node cluster, and if one of the EPRS server goes down, as we can see that EPRS server 1 is down, then the EPRS framework will auto detect the failure through the use of the Zookeeper, and the associated publication and subscriptions will be failed over to the next EPRS instance. So as you can see in the diagram that the DB1 is after the failover, DB1 has been failed over to be managed by the EPRS server 2. This is another extension. So it handles all the different failure scenarios. That includes both the failure of EPRS server itself as well as that of the database server. So as Marc pointed out, one can ensure the write availability by using configuring multiple writable databases. So for example, here we can see that the EPRS, the DB3 server, the DB3 database goes down. And at that point of time, it has consumed data up to offset 2. And there was data at offset 3 that was yet to be replicated. And at that point of time, database server goes down, or there is a network disconnection. So what happened is that, as I pointed out earlier, since Kafka maintains an automatic replication, so the relevant topics are replicated across the whole cluster, and data will remain there. So as we can see, as we can see here, once the database is down and then data is being generated by the other databases, that data will remain in the Kafka topics, and it will be available till the point when the depending upon the retention policy. So it is recommended to set a high retention policy. The default value is 7 days, but one can increase it depending on the specific workload and the use cases. So as long as data is available at the Kafka level, and once the DB server joins back, then we can see that it will resume from the last replicated point. So there is no loss of data, and at the same time, we don't need to maintain the data at the change data at the database server level. So basically, for example, in case of PostgreSQL, the data change capture is managed through the use of wall log. So those wall log files obviously need to be recycled. Otherwise, if you keep on actually retaining the log files, the database server disk space might run out of space. So what happened is that although the DB3 is down, but in the meantime, the Kafka will replicate data to the other databases, and it will send acknowledgement back to the source publication database so that it can recycle the wall data, because now we have the specific change log available at the Kafka level, and that is being maintained in a fault tolerant way as it is available on redundant replicas. So once the down database joins back, then it will resume from the last failed point, and everything will be up and running again. So as Mark pointed out, our existing solution provides heterogeneous replication capabilities. That includes replication across open source PostgreSQL as well as EDB database server. In addition to that, we have provided the replication capabilities from Oracle and SQL Server. In the EPRS 7 first release, currently it provides replication support for PostgreSQL as well as EDB Advanced Server. And then in the next release, in the next near future, we are planning to provide the replication capabilities for Oracle and SQL Server. In addition to that, as I pointed out earlier, we have a plan to provide the flexibility to plug into the existing Kafka and Zookeeper clusters. DDL change replication is the capability to take care of any changes in the publication tables in terms of the new column additions or column removal. And then obviously one of the key reason for using Kafka is the its flexibility in terms of the data integration, where one can define any type of source and data points ranging from the relational database systems to the big SQL and NoSQL data sources and data targets. So we have a plan to provide certification with certain key players in that area to enable the analytical usage of the data. So before actually I can go to here, we can have the discussion around the beta availability and other thing. I will now switch over to go through the demo. So in order to, since there is plenty of stuff to cover, so in order to actually optimize the time usage, I have already installed and configured EPRS on my system. So in order to simulate a 3 nodes cluster, I have set up the servers that are running on different ports. So I have already started the 3 EPRS instances, as you can see here, and we can see through the rep CLI, we can list down the servers that are part of the replication network. So I can quickly go through the steps that were used to start the servers. So once the servers are started, then you need to form a network. So the first server that joins the network, that becomes by default the leader server, and later on you can add as many number of additional nodes as required. After the first server, the password is set, and then after any subsequent action will require an authentication. I've also added one database that is registered with the first server, and next I will proceed to register the 2 other databases. So I have set up 2 database servers. One database server is running 2 databases, and the second database server is running the 3rd database. So that will also help us to see some of the failover cases. So I'll proceed to register the second database. So as you can see here, the add db command is the one that is that is used to register the database. You need to specify the server that will be used to manage that database, and that is followed by the credentials. So the second database is also registered. Now we will register the 3rd database with the 3rd EPRS server. Sorry, just a minute. So we'll register the third database. Sorry. So as you can see, the third database, that is ngx pgbench_node3 is registered with the third server. Now we have registered 3 database servers. The next step is to create a publication. So depending on your requirement, if you are going to create a master replica, then you will create a publication only on the first database server, and then the other nodes will join in the consumer mode just to read the data. Otherwise, if there is a requirement to set up a MMR cluster, master configuration, then the publication will be created from one of the database server, and then each of the joining node will act both in the read and write mode, so that once these target database joins, then there will be both a subscription and publication created on that database as well, and that will be happening behind the scene. So let's proceed to create the publication. So for example, here is the command that is used to create the publication. You need to specify the number of tables. If the requirement is to just include a subset of tables, you can make use of -tables command. Otherwise, if the requirement is to include all the tables, you can opt for all tables. So in this case, I have set up the pgbench database that is seeded with the default scale, and it is roughly 20 MB of database, and I have included all the tables from that pgbench database. So we can confirm if the publication is created and the tables that are part of that publication. There is a list pub table command that we can use to see. So we can see here that we have a publication that is named ngxpub, and then there are 4 tables that are part of that publication. So the next step is to define the target consumers both. So we can opt to either, as I said earlier, we can opt to just have the replicas, or we can have the master, or a combination of both. So in this, for the demo purpose, I will proceed to join 2 additional databases that will act as a master. So we have a join pub command. So since the second server is identified through this ngx_node2, so you need to specify the server name and then the database ID that will be used as the target master. This database is already registered, and then there is the publication name, and this is the key thing. I mean, you need to specify the node type. So RW means that this database will act as a master. It will be consuming changes that will be available from other master nodes, and it will, at the same time, it will also be publishing its own changes through the parent publication. Next, we will register the third database. Sorry, we will join the third database as the master with the given publication. Okay, so just a minute. So we will join the, so this is the third database that will join the publication to form the 3 node cluster. We can quickly see the make use of the list consumer to see that how many consumers are there and how many masters are there. So as you can see that we have all the three nodes that are basically acting both as a master and as a replica. The next step is to perform the snapshot so that the target databases, I mean NGX, PGBench, Node 2 and Node 3 databases are seeded with the initial set of data that is available on the source publication database. So we will perform an online snapshot. We also have the option to perform offline snapshot in case the database size is bigger than it's recommended to make use of the offline snapshot. For now, I will proceed with the online snapshot. It's a fairly small database. So first, we will perform the snapshot for the DB2. And then we will proceed to check if the snapshot has been completed. So it is still in progress. It should be done in half a minute or so. Okay, while it is in progress, we can see if the data is available in some of the tables in the target node. So we can connect with this database and confirm the size of the data. So we can run certain queries. Okay, it is completed now and we can proceed to see there. Okay, as you see, we have the data available in the relevant tables. So we can confirm with the other tables as well. Okay, next we will proceed to perform the snapshot. So now in this case, it has taken a bit of time, but next as I will perform the snapshot for the third database, then it should be quick because the data is already loaded in the Kafka queue. So this time the data won't get, will not be pulled from the source database. So as you see, for the third database, it quickly got completed because the data was already loaded in the Kafka queue. So that is one of the advantage that I mentioned in one of the slide, that the data is reloading is saved in this case. Next, we will start the streaming so that we can observe the change dataset replication. So once this teaming is started, then I will launch a small PG bench session initially, just to see that I will simply run a 30-second run to see that changes get replicated across all the databases. And then I'll run the validator to confirm that the data is same and consistent across all three databases. And then that will be followed up by a failover scenario that I will demo. So now we can launch the PG bench session, and at the same time, before I do that, let me start the. So here we can run the. So basically, a latency command that will help us see what is the latency. Although it's a single system that is running everything, but otherwise, I mean, purpose is just to show that one can measure the latency. Again, similarly, we can do the same on this third database. Now I'll proceed to run the PG bench session for just for 30 seconds. And now we can, as you can see, that this is the latency is roughly half a second or so. On a related note, we had conducted the benchmark on a formal AWS environment, and we were able to have a latency, a consistent, sustainable latency, roughly around half a second, with the TPS rate of 3000. So once the PG bench session finishes, and I will run the validator to confirm that everything okay, that is done. And we can see here that now it is consistent latency. It means that everything is in place. We can quickly run a validation tool. So that will actually, as you can see here, we can compare the data across database 1 and database 2. So as you see, the data is same. It says that all the rows are consistent across both the databases. Next, I will quickly, I think we are probably running short of time, so I'll quickly proceed to demo the failover case. What happens if the database server goes down, and what happens if the EPRS server itself goes down. So first I will demo the database server scenario. So I'll run another session, a longer session, and so this time I will run it for more time, for 5 minutes or so, and then in between we can see that initially the data will be replicating across all the database servers, and then I will bring down one of the database and then join it back to see that it catches up from the last point. So let's start it here. And so while it is replicating, I'll bring down the database 2. So I'll stop this database, and we can confirm it here as well that this database is actually down. So if I try to connect on this port, it says that database server is down. So we will just wait for a few seconds, and then I will brought up that database server again. So let's start this server. And now let's get back to that. Now we will try to, so we have reconnected. We will run the same latency query and see. So as you see that this varying value indicates that the replication has resumed back. Just to confirm that the data is consistent, I will proceed to stop the PG bench session so that we can see that all the databases are consistent. Now it's almost same latency. So now we can run this again to see if data is consistent. So as you see, the data is valid across, data is consistent across DB1 and DB2. Now the next step is to showcase that how the single point of failure is addressed around the EPRS server itself. So I'll simply bring down one of the EPRS server so that the attached database will be taken over by the other servers. So what I will do is that I will simply, just a minute. So I'll run a session, another pgbench session, and then we can see that the data is being replicated. Now I'll simply stop one of the EPRS instance. So let's stop EPRS 3. Now the third database for a while will, as you see that we can check the database status. Okay, just a minute. So we can see that it has, it has resumed back, and the data is again being replicated on the third database. Okay, I see that it is, again, it is doing it. Okay, so what I will do is that now I will quickly stop the pgbench session so that we can confirm that the data is consistent after this failover. So I'll stop the pgbench, and then we will proceed to again run the validation. So let's run the validation once again across 1 and 2 and 1 and 3 as well. I'll also do that. So the data is consistent across 1 and 2, and similarly we can check if the data is consistent across 1 and 3, because 3 was the database that was switched over from EPRS server 3 to EPRS server 1. So let's do that. So as you see, the data is consistent across all 3 databases. So we have seen that it doesn't matter if the database goes down or if one of the EPRS server goes down, replication resumed and data was consistent again. Just final slide. So we have we have recently released the first stable version of EPRS 7, and that is available for non-production evaluation. In case it satisfies the requirements for your workload, then you can proceed to engage EDB to enable the production configuration and qualify it for production workload. Expected GA is roughly estimated last quarter of 2019. That's it from my side. Over to you, Mark.
Okay, good. So thank you, Zahid. And we have a little bit of time left for some questions. Courtney, can you walk us through the questions?
Sure. So one that came in, does EPRS work with open source Postgres, or does it only support EDB Postgres Advanced Server?
So EPRS supports both open source Postgres and EDB Advanced Server. Zahid, you want to add something?
Yeah, definitely. I mean, since we are based on open source, so whenever we provide certain capability, it is available both for open source as far as the EDB Advanced Server. So it works for both databases.
Okay. Another question that came in, how many EPRS servers do I need to create a highly available replication infrastructure?
Yeah, so the minimum recommendation is to run 3 EPRS servers, although you can, in a non-production environment for your evaluation, you can even run a single EPRS server, but for the production, the minimum requirement is to have a 3 EPRS configuration. Yeah, Mark, you want to add something on top of it?
Yeah, I mean, the reason is basically for everybody to understand. We start with 3 servers, and even if we lose one, we still have high availability, right? If you started with 2 servers, you lost one, you in fact have lost high availability. So for many production environments, that's not sufficient anymore to continue. So that's why starting with 3 is the better way to do it. And also, that makes the leader election more powerful, because now you can have a quorum in the vote.
Okay, it looks like we have time for one more. So is EPRS the same thing as second quadrant BDR?
No, it's not. In fact, EPRS provides more filtering, and EPRS also, EPRS 6, the current production version, also allows replication from Oracle and SQL Server, and EPRS 7 will also provide that soon. So basically, second quadrant BDR is limited entirely to PostgreSQL, and EPRS is really focused on supporting all the scenarios that we talked about before, ranging from migration to offloading workloads that currently run on Oracle, to then providing quite complex heterogeneous replication scenarios, and BDR is much more limited.
And obviously, I would like to add the use of Kafka actually helps us actually extend it to accommodate more and more domains, specifically in the domain of analytics, as well as extending the boundaries around different data sources and data ends. So it's not just limited to PG, but extensible domain.
Okay, thank you. I apologize for all those questions that we were unable to get to today, but as a reminder, we will follow up with answers via email. Thank you all for joining us for the webinar. We'll be sharing this recording along with the slides with you via email as soon as possible, and we hope you all have a great rest of your day. Thank you.